Hello learners, welcome to the course on deformation processing of materials. In this course, we will see various techniques and tools used for the deformation processing or metal forming so that the metals can be transformed or can be given useful shapes or can be converted into useful components for various engineering applications. We will see the fundamentals of various processes, the process parameters, and in many of the cases, which are the probable defects. So let me introduce you with the fundamental definitions of these deformation processing, or what basically the term deformation processing means. So metals are basically very widely used due to their easy capability of being transformed into useful shapes such as rods, billets, blooms, and sheets, etc. So this transformation can be achieved in two different ways. Basically, metals can be given useful shapes through two ways or by two ways. So these two ways are by plastic deformation and the other way is by machining or removal of metal, machining operations. Okay, so what happens in this case of deformation? By plastic deformation, what we can do is basically the volume and mass of the metal or component, initial component, is kept fixed, while metal is displaced from one particular location to the other so that the component can be transformed or can be reshaped into the useful form. So here mass and volume remain constant and metal is displaced. Okay, and by this way, various components are produced or formed. While in case of machining operations, metal is chipped off or is removed. Metal is removed. Okay, so the initial component which is used for these processes, which finally gets converted to the final product, the in the initial stage it is called workpiece, or even during the working process, the component which is being worked upon is known as workpiece. So during these particular operations, we need to keep in mind the mechanical properties of the final component or final finished product also. So importance should be given. Importance is given to mechanical properties of finished product. Finished product. Okay. And the part on which various operations are done is known as workpiece. So these are some important points. Now, these metalworking operations or metal forming operations can be classified into different categories or different types. So broadly, based on the stresses applied, these are classified as in five different categories. Okay, so these categories are categories of metal forming, not operations, these are processes. Okay, so they are basically direct compression type, direct compression type. Then the next one is indirect compression type, indirect compression type. And the third one is tension type. The next category is bending type or bending process. And the last category is shearing. Okay, so let us see how these operations basically are done, or let us try to understand them through some schematics. Okay, so direct compression type operations basically mean that the forces or stresses are applied onto the workpiece surface, and the metal flows at right angles to the applied stress. Suppose stress is applied from the top, then the metal will flow in the lateral direction, means this perpendicular direction. So this type of operations will involve metal forming process like forging. Okay, so forging, we will see many of them, these processes in detail. So schematically, forging is, let me change the color. This is done like, suppose this is my workpiece. So this is kept on some support, and then a die applies. I should not call it a die, it is basically a type of punch which is used to apply stress from the top or any other, it can be in any direction. So basically it applies force onto the surface of this workpiece, and this workpiece then flows in these two directions. Okay, so this operation is known as forging. Here you can see this is direct compression type process. So compressive stresses are being applied from the top and bottom. Okay, so now the next one is a similar process, which is rolling. Similar means direct compression type here. Okay. So in the rolling operation, what is done? Suppose this is my workpiece. So various rollers are used to apply compressive loads these rollers rotate like this, and the workpiece now, due to the application of stress by these rollers, flows like this, and its cross section gets reduced. So it was initially like this, and this is my finished product from the rolling operation. Okay, here you can see stresses are being applied here at these points. So this is the rolling operation, which is also a direct compression type operation. And next one is, let us see what it was indirect compression type. So in the indirect compression type process, the compressive stresses are not directly applied onto the workpiece. Actually, some sort of tensile stresses are applied, due to which the resultant or means lateral forces which are developed are of compressive nature and are very high in magnitude. They ultimately lead to the deformation which we want, or the change in shape that we need. So the next process is wire drawing, which is a type of indirect compression type process. Okay, so let us see wire drawing. Wire drawing, it is now a type of indirect compression type. Okay, so wire drawing, how it appears. Here the initial long strip or rod is fed into the die. There are dies like this. This is my initial workpiece. This is fed here, and here compressive stresses act, which lead to the reduction in cross section of these. And on the other side, this is pulled with tension. Okay, for clarification, let me indicate this flow with some other arrow, so that people don't get confused, like this is a tension type force. So this was indicating the direction. Here it is indicating the tensile stress. So here tensile stresses are applied, and this was the die. This was the die material. Okay, so you can clearly see that application of this tensile stress leads to compressive stresses over here, which leads to the final deformation into this workpiece, and we get wire type of final or finished product. So this is wire drawing. Another process which is similar in nature and is of indirect compression type is extrusion. Okay, so extrusion is another process. In extrusion, what we do, let us see the schematic. Again, suppose this is my workpiece. So here again there are dies. Okay, and these are dies. This is what happened here. This is the opening from which metal can flow, and the remaining portion is blocked by these dies. Now from here, this is pressed, and from here it is allowed to come out. Okay, so when this material is pressed from here, the compressive stresses acting here cause it to get reduced in cross section, and ultimately the finished product of reduced cross section comes out from here. This process is called extrusion. Another process is there which falls in the category of this indirect compression type process, which is known as deep drawing. Deep drawing is sometimes also known as cup drawing because this process is used to form cups. So it basically appears like suppose this is my die. Here die and punch are used. Okay, so this is the die, and suppose this is my workpiece. Why I have drawn, you'll get to know in a moment in this way. So suppose this is my workpiece. Here a punch tries to push it down. I should not say tries, basically we intentionally press it using this punch in this direction. So what happens here is that at this point of contact, the stresses act onto the workpiece, and here it is clamped, so this remains fixed and is not allowed to means move in this particular direction like this. So what happens? This workpiece takes the shape of this die, which is in the form of a cup, and ultimately the final product is in the form of a cup or glass. So this is known as deep drawing operation. This was the type of indirect compression type processes. Another category now is the tension type process. So in tension type process, tensile forces are applied to lead to the formation or final shape of the component. So how it appears, let us see. So now we are seeing the tension type process in which we can see the stretch forming operation. Stretch forming operation or forming process. So in this process, there is some periphery or punch or component like this onto which the workpiece is stretched using tensile forces. So that it can take the shape of this and finally get wrapped onto the contour of the die. So this is the die and these are the tensile forces. So this is stretch forming is a tension type metal forming operation. Now the next category was bending and shearing. So here in bending forces are applied, and in shearing, shear forces are applied. So how they appear? Bending appears somewhat like we have a sheet and we have a die, then we again have a punch. Here this punch tries to bend it down. So this is the compressive forces acting here. So this is the bending type operation, and in shearing, shear forces are applied. Okay, so in shearing, how it appears? Suppose this is my workpiece. So it is supported onto a die like this, and another one is like this, and here the shear forces are applied which try to shear it down the workpiece. This is the workpiece. Okay, so This is the shearing type of metal forming operation or process. So this is the type or classification of these metal forming processes based on type of stresses applied. Based on the type of workpiece also, we can classify them into two different categories or two different types. So this was on the basis of stresses. Now if we see on the basis of type of workpiece, uh, on the basis of type of workpiece, we can say that metal forming can be classified into bulk deformation and sheet metal forming. Okay. Bulk deformation and sheet metal forming. Okay. These are further classified into various categories. So the bulk deformation can be classified as rolling, because these operations are done onto a bulk sample or sample like bloom, billet, etc. So the entire bulk is deformed. So rolling, forging, extrusion, uh, de wire drawing, wire drawing. These are type of bulk deformation processes. And sheet metal forming, this can be classified as bending. Bending is a type of sheet metal forming operation. Bending, then cup drawing or deep drawing. Cup drawing or deep drawing. And one more is shearing. Shearing also falls into this category only. Okay, so this is the classification of these processes based on the type of workpiece being worked upon. Okay, so this was the classification of various processes. Now, let me draw a schematic of various regimes or regions of the workpiece or the entire setup at the particular location where this deformation process occurs. Okay, so let me draw that schematic. So it somewhat appears like, suppose this is my workpiece and these are the tools which are causing the deformation. This is the undeformed region, and suppose from here it is getting deformed, so this region is deformed. Okay, this region is deformed, and these are the tools. This particular location, this will be the deformation zone. not the deformation zone, actually the zone where this workpiece comes into contact with the tools, and here some sort of lubrication and will be used because there will be a lot of friction between the workpiece and the tools or dies. So this is lubrication system or lubrication zone. Okay, this particular region is deformed already. Also, there will be a flow of heat. Actually, this suppose there is a movement, relative motion between this workpiece and the tool or die. So there will certainly be some friction acting over here. Frictional forces will be acting. Here also friction will be there. And due to this friction, there will be generation of heat. So this heat will get transferred to the die or tool from the workpiece. So there will be a transfer of heat also, which will ultimately go outside the system. And from here, finally, we will get our product. So this will be our product. This region, the deformed zone, will have a lot of stress and strains acting at this particular zone. So they basically determine which type of operation it is and which are the parameters which can be controlled to optimize the process and so on and so forth. Okay, so this was the overall system. So let us now see some of the terminologies or component types which are frequently referred to during the metal forming process, and we will define some of them. So let us first see what is a bloom. Bloom generally has a square cross section, and this is the first breakdown of an ingot. Okay. Bloom is a first breakdown of ingot, and it has a cross section of about 160 mm by 160 mm. Or if you see in inches, it will be approximately 6 inch by 6 inch. Okay, so this is a bloom, and it appears like a cuboid shaped component which has a cross section of about this dimension, that is 160 by 160 mm square. Okay, so this is a bloom. Now the next one is a billet. Billet has cross-sectional dimensions, or a cross-section which is less in the dimension as compared to bloom, and it has a cross-sectional area which is generally greater than 40 mm by 40 mm. Okay, it also has a similar appearance, but it somewhat appears longer as compared to the bloom due to the lower cross-sectional area. So this is something like this. This is billet. Next one is slab. So slab is nothing but hot rolled billet. Sorry, hot rolled ingot. Okay, and it has a cross-sectional area. Cross-sectional area which is greater than 100 mm square. Sorry, 100 centimeter square. Okay, so this is a slab. We will see a little detailed information about this. So there are some mill products. Okay, so mill products. What are these mill products? So first one is plate. We'll write it clearly. This plate. Okay. So what is a plate? Plate has a thickness which is greater than 5 mm. The next one is sheet. Sheet, and it has a thickness less than 5 mm, but its width is greater than 600 mm. 600 mm. Okay. If the thickness is less than 5 mm and width also is lower than 600 mm, then it is known as a strip. Strip has a thickness less than 5 mm and width here is also less than 600 mm. Okay. So this is the classification of mill products. Now let us see what type of deformations can occur in the materials or metals during this deformation process. So one is elastic deformation. You might be knowing this very well, what we mean by elastic deformation. Okay, so elastic deformation is nothing but a reversible type of or recoverable type of deformation which is removed or reversed when the applied stress or load is removed. So this is, it is recoverable when stress is removed. Stress is removed. This is not a permanent deformation. It is a temporary type of deformation. So it is not permanent deformation. Okay. And this phenomena is generally observed before the yield point of the workpiece or material. Before yield point. Okay. So this was elastic deformation. Similarly, there is plastic deformation. So what happens in case of plastic deformation? Plastic deformation. So in case of plastic deformation, the deformation is a sort of permanent type. It crosses the elastic limit or the yield limit of material and it remains even after the stress is removed. So this is a deformation beyond elastic limit. Deformation beyond elastic limit. And this occurs due to various phenomena like slip or dislocation movement, etc. Okay, so occurs due to slip, dislocation movement, etc. Dislocation, movement, and through grain fragmentation and other phenomena. Okay, so this occurs, as I told earlier, in the plastic region, and it follows a flow curve type of behavior. A flow curve is needed to define this characteristic of the material. So this is in plastic region, and the behavior of material, behavior of metal. We are talking mostly about metals here, so behavior of metal is expressed by a flow curve. So if we are talking about flow curve, then we should know what does it mean and what flow stress means basically. So flow curve basically involves flow stress, and flow stress is the stress which is required to cause a material to deform under the applied stress or to flow continuously under the applied load or stress. Okay, so this flow stress occurs beyond the yield point or beyond the yield stress. So flow stress, flow stress means it is a stress beyond the yield point at which the material keeps deforming or keeps flowing. At which material deforms plastically. Deforms plastically. Okay. And it is the type of instantaneous stress. So for a particular moment or for a particular say strain or position on the flow curve, the flow stress is fixed or flow stress is defined as a particular value. So this is, in other words, we can say that an instantaneous value or instantaneous value of stress which is required to keep the metal flowing or continue the forming of metal. To continue the forming operation, forming of metal, and to keep it flowing. Okay, so this is the flow stress, and mathematically it is expressed as flow stress is represented as K epsilon to the power n. This is not m, this is n. Okay, so where this YF is the flow stress itself, and K is known as strength coefficient. Strength coefficient. Epsilon here is the true strain. true strain developed into the material, and N is known as strain hardening coefficient or work hardening coefficient. So this is strain hardening coefficient. Okay, so these were some fundamental things which we need to know before knowing into the knowing the details of various forming operations. Okay. Also, there is a term which is frequently used in these operations or these processes, which is known as the average flow stress. Average flow stress, and this is obtained by finding the average value of this. So I'll not go into the derivation, I'll write the formula directly. So this is represented as YF bar, and it value comes out to be K epsilon to the power n over n plus 1. Okay. So this is known as average flow stress. Now, as we know, we have seen the relation for flow stress and average flow stress. Let us work out on some numerical examples so that we can easily get or grasp the things over time. Okay, so here we have an example. So let me write it down with some different color. So we have an example. Okay, so here we are given that this strength coefficient K is 550 MPa, and the strain hardening coefficient is 0.22. During forming process, the final true strain which is observed in the material is given as 0.85. Okay, so during forming, final true strain is epsilon is reported as 0.85, 0.85, and we know the relation of flow stress, so we need to determine the flow stress and the average flow stress. So the flow stress we know that is given by K into epsilon to power n. We directly have to substitute the values. So K is 550, epsilon is given as 0.85, and n is the power here, so n is 0.22. And if we evaluate it or calculate it, we get the value as approximately 531 megapascal. Unit will be that of K only, because here strain is unitless, and any unitless quantity raised to any power is also unitless. So this was flow stress, and the average flow stress will be average flow stress YF bar is given as nothing but this K epsilon to power n, that is flow stress divided by n plus 1. And if we substitute the values, we get 550 into 0.85 to power 0.22 over 0.22 plus 1. And upon calculation, we get this value as approximately 435 megapascals. Okay, so this was an example which utilized the concept of this flow stress and average flow stress. Okay, Let us see another example. So again, there is an example. Okay. So here we are again given with K value as 850 megapascal and N value is given as 0.3. Okay. Now, in this case, in place of strength, they have given us the data like initially the specimen was like this. Okay. There was a specimen like this, and this is you might have seen this in your course related to mechanical behaviors, that this region is known as gauge length. So gauge length here, let us say this was L0, was given as 100 mm, and after elongation we got the final length as 157 mm. Now we need to find the flow stress and average flow stress in this case again. Flow stress and average flow stress. Average flow stress. So how should we approach now? We need to calculate the true strain first, and then we'll use the relations we had seen earlier. Okay, so we know that true strain is given as true strain is epsilon is nothing but ln of initial length by final length. Uh, Sorry, this will be final length by initial length, because this epsilon is written as ln of e plus 1, and if we back substitute the value of e, which is engineering strain, we get this as final length by initial length. Okay, so if we substitute the values here, ln 157 by this was 100, so this comes out to be approximately 0.45, I think. Yes, it is 0.45. So now we have the true strain value. Therefore, flow stress here will be K epsilon to power n. Okay. So if we substitute the value, K here was 850. Epsilon comes out to be 0.45 and n is 0.3. So upon calculating, we get this as 669 megapascals. Similarly, we can calculate the flow stress, average flow stress here. So average flow stress is, this is YF bar. This is nothing but K epsilon to power n over n plus 1. Okay, so upon putting the values and calculating, this is 850, this is 0.45 to power 0.3 upon 0.3 plus 1. This value comes out to be around 514.6. Okay. So this was another example. Now let us see a small concept related to the elastic recovery, which is observed during the deformation of materials. So let us see. Let us look at it very briefly. No? So it will be elastic recovery. So suppose if this is the stress strain diagram of a material, this is the applied stress and this is the strain here. So suppose if I load the material, and after the yield point also I keep the material deforming. If I had removed the load here, it would have come back again. It would have retraced this path, and you would be knowing very clearly that this is the slope. This here is defined as the Young's modulus E. So if I had removed the load here, material would have returned on the similar path to initial value of strain, which is 0. But suppose if I've loaded the material to this point and then I've removed the load, then again the material follows a path like this. So this was the strain which I had given to the material. Let me let me call this point as A. This is B. This is C. So here in this region, I had strained the material to the strain. Say this is O, then OA is the total strain that I had imparted or given to the material. But after the removal of the load, this much amount of strain the material has regained, or not regained, actually it has recovered from this strain. Again the slope is same here, the slope of this line, because this path is parallel to this initial path. So again the slope will be Young's modulus of elasticity, and this region, let me divide this into two regions. So basically this is strain and this we have divided into two regions. So this region, this particular recovered part, this is known as elastic recovery. This is due to the elastic behavior of material, that after removal of the load, the material regains its original dimensions or recovers the strain, elastic strain. So this is elastic recovery or spring back. And this is the permanent deformation. Okay, so this is permanent deformation. Again, to understand this concept more clearly, let us see an example. Okay. So let us see an example here. Suppose I have a bar with initial length of 100 mm. Okay, this was of 100 mm initially. Now what I did, I suppose I compressed it. So that it becomes this much. Okay. So this height has now become 95 mm. Okay, and then I remove the load. So definitely there will be some elastic recovery into the material, and now its length will be this. So I need to determine the final length of this material. This value I need to determine. Okay, and this much was the recovery here. This is the recovery. I'm given with some properties or fundamental characteristics of the material and loading conditions. So the applied stress here was 500 into epsilon to power 0.10. Since this is a plastic deformation, so this will be a type of flow curve relation. This will be a power law relation here. Okay, so and the strain value is epsilon here is true strain. We'll have to work on it so that we can get the final dimension. This is true strain here. And the Young's modulus or elastic modulus of material is given to us. This is 200 GPa. 200 GPa. Okay. So let us try to find the final length after this recovery, elastic recovery. So now we are given with initial length as 100 mm. Final length we don't know, but this process, entire process is occurring in two steps. Let us say the first one is compression till 95 mm and then elastic recovery after the removal of load. So let us consider the first part itself or first step itself, and temporary final length, let us say this is 95 mm. So in this case we can find the true strain for this particular first step. So this will be nothing but ln of final length by initial length, and this is nothing but final length here is temporary one. Final length is 95 and initial length is 100. This value comes out to be minus 0.051. Okay. So it should come in negative because this is a type of compressive load. So the length is decreasing. So definitely true strain should be negative. So and it comes out to be negative. But if we now if we substitute this into the relation of stress, we will have to use the magnitude only. Okay, so we will not take the sign here. So in this case, sigma will be minus, no, sorry, not minus, this will be, this was 500. Okay, so this becomes 500 into 0.051 to the power 0.10. Yes. So if we calculate it, this comes out to be approximately 371.3 MPa. This is given in MPa. Okay, so this is the value of stress we get. Now this stress would be compressive stress. Since we have not taken the sign, so we are getting like this. Now we have the stress value. Again, now let us consider the second step. Since this is an elastic recovery, elastic type of deformation, so here the Hooke's law will be valid. And again, if Hooke's law is valid, then what is the relation? Sigma is nothing but epsilon E or E epsilon. Okay, so here here let us put the values. This is 371.3 and this is 200. This is in megapascals and if, this is in gigapascals. So if we convert this also in megapascals, we will have a multiplying factor of 10 to power 3, and this strain will be nothing but, this is this should not be, this will be E here, or yes, this is E. Okay. This will be change in length by initial length. Since I have written E, it should be true strain, but since these values are very small, so we can consider them to be approximately equal, the true strain and the engineering strain here. if they are very small, they can be interchanged with each other. Okay, so I have written the engineering strain here, and it will be changed in length by initial length. Now here this strain is for the second step, that is this initial length here will be 95, and final length or the change in length will be this recovery that we want to calculate now. So this is nothing but temporary LF. Okay, so now let us put or substitute the values. So here, from here we can get delta L as 371.3 over 200 into 10 to power 200 into 10 to power 3 and multiplied by this LF prime. Okay, so this delta L comes out to be approximately, I've calculated this comes out as 0.1763 mm. So this was the increase in length of the recovery, increase in length due to the elastic recovery here. So this was the recovery part. Therefore, final length will be LF will be 95 plus 0.1763. So this is nothing but 95.1763 mm. Okay. So this was an example to elaborate the concept of elastic recovery taking place. So with this, we will close this session, or we will end for today. And from next lecture onwards, we'll try to look various operations or various metal forming processes. Thank you.